much. I'd now like to introduce Dr. Martin McIntosh, who is full member and program head of computational biology at the Fred Hutchinson Cancer Research Center and at the University of Washington Comprehensive Cancer Center. His research primarily focuses on immune-based diagnostics and detect imaging.
Okay, thanks for that. So the last speaker pointed out that he works at the NCI, but it's a personal opinion. Since I don't work there, there's no harm in me saying that my opinion really is the NCI opinion. So there's actually a way to do the full, you can do this. I give a PDF file, so there's a way of doing full view, I think, right? I can give Chris Berg's. Okay, yeah, so yeah, this is I'll just start. I was asked to give a talk on imaging, and I think the way I'm going to think of this is really kind of more like technology than imaging, and maybe even sitting back and say, well, if you take a step back and think about what happened over the last, say, 15 years or so, at least my failed career trying to make a difference in early detection, what's the best way forward, and how to do that in a way that actually might benefit women most. So this is information. So there's the subtitles, and just talk earlier. Someone made a comment I thought really funny. I was a PhD trained statistician one time, and I was once a statistician back before we became useful. And do I hit the next slide? Is there a button up here I hit? Okay. So I think let me start off by pointing out that how important I think that it's essential to actually tackle the imaging question for early detection. A lot of the funding has been focused on early detection biomarkers, but it just can't work without better imaging technologies. And I think the PLCO and other studies have shown that TVS just won't be adequate. It could be that some of the markers we have actually might be useful, but unless you can actually localize any lesion to the ovary, you're kind of out of luck. And this shows an example. This little scatter plot that's hard to, this histogram or whatever the box, whatever those things are, sticks are. Give an example of this. So if you look at a lot of the studies, p53 is often looked at as a good ovary cancer marker or for other diseases. And a lot of the studies, they'll compare tumors to healthy women, and they'll say, look, it's 30% sensitive and almost nearly perfectly specific. But that's in a world if people only got one cancer, and if they didn't have cancer, they were healthy. It also turns out it's been reported as a marker for about 23 other cancer sites. This actually takes a summary of those and puts them together and combines with the SEER data and looks at little different bars. The bars furthest over to the left give the US incidence of each cancer. So ovary cancer is the third one over. The next bar gives I believe it's the sensitivity of p53 autoantibodies in that tumor, right? So basically it's 25% sensitive, right? The next bar over, which is tiny in ovary, this basically says what's the percentage chance of if a woman who has cancer has a p53 autoantibody, what's the chance she has ovary cancer? It's pretty small, right? So how can we say that something's 99% specific when if it's a positive test and you have cancer, there's a vanishingly small chance you actually have cancer. And this doesn't include the number of people who actually have p53 autoantibodies because they have benign conditions or some condition. p53 and other autoantibodies typically arise because they're tumor necrotic products. Oftentimes people think that they actually arise earlier as part of injury, and they're just kind of re-stimulated when there's actually necrosis. That actually the autoantibody response could have actually occurred earlier, and there's a B cell response to it. And the last little dot, the little tiny little vanishingly dot, kind of says, well, imagine a woman who's actually in an ovary cancer screening program and gets a positive test. What's the chance she has ovary cancer? And it turns out it's tiny. So p53, no matter how abundant it is, it's actually a test for lung cancer or colon cancer because it's just the prevalence is so much higher. So this can be the same true for ovary cancer and everything. That just to show how far we are from doing diagnosis is the fact that the way we do studies is we only think of worlds where people either have one cancer type at all. And most CM25 is also not an ovary cancer marker. It's a marker of large numbers of other diseases, but not ovary cancer, right? Because you're more likely to have other cancers instead of it. Except, unless of course you had an ability to actually localize it, right? So what you would do if you had this practice, when one had a positive screen, you would go down probably you would start from the ones that were most prevalent, the kind of the third bar that's highest. Or you would start with the ones that are most easily visualized. So if you ever want to use any marker for ovary cancer that's promiscuous, right, unless it's like PSA. PSA comes from one organ, right? That's why it's valuable, not because it's a good marker or a bad marker. It has to come from one organ, so it localizes it. All screening strategies that work localize the tumor by imaging, visual inspection, or some otherwise. And we can't do that with ovary cancer. well enough to match any marker. We think about the size of the tumors we need to find based on these studies where you remove tubes. No imaging test can work. So what you're going to end up having is telling a woman that she has some this potentially kind of promiscuous marker growing, and you say, well, we'll have to wait till this thing's big enough to be seen on sonography. Or you take her tubes out, right? That's going to have a high risk rate. It turns out you contaminate that high risk rate, then you can, well, why do you even have to wait for the marker to occur, right? So the thing is that it can be helped dramatically by having imaging. And the thing is that there's actually been a lot of advancements since in the last several years on how to do imaging. And so I'm just going to mention those a little bit. So if you turn to the next slide, please. If you can, yeah, so nanoparticles. So there's a whole world of engineered particles. This is a picture of them. There's a citation on here somewhere you can look at. Nice little article. All kinds of nanoparticles have all kinds of properties that help them get inside of different tumor microenvironments and can be optimized. And they can be, actually, they have different properties that resonate if you heat them or put light on them or you shake them or do all kinds of stuff. And but they're small enough they can get through, again, that term I always mispronounce it, exasperate through the vessels, right? Extravasate, right? Through the vessels, and then get actually to the surface of the tumor. So there are things like microbubbles that get through the vasculature. This can go to the surface of a cell, right? So you can image the cell, and you can conceivably get down to a few millimeters with ovarian cancer. I think with a probe. There's a guy, Sam Gambier, who all my IDs I steal from, and he claims it's about the size. I have to say though that when he heard the first studies of the people removing tubes and seeing these small lesions that later recur with ovarian cancer, he basically said, "I don't think we can do that," right? So it's a little thing that, maybe the lesson is that there really is no such thing as an early curable stage, which is a thing we have to cope with later, right? I'll talk about later. So you can picture these things from a large family of things. You can get right to the tumor, and you can localize it. In fact, these things can be shared. If it turns out, a promiscuous blood marker is a bad thing, but a marker that's in the cell surface of ovarian cancer but is also on breast cancer can be reused, right? So there's just a lot of value for this. Of course, it's just these things also have a lot of engineering and industry behind them. So there's people in industry pushing these things through to FDA approval. I think it might be true that people would say that FDA approval of these things in someone's body will be inevitable. I don't know if that's still the case, But so let's go to the next slide a little bit, right? So this is kind of the evolution of my career, and maybe it's what I'll use. So you start off with early detection will save lives. Early stage cancers live longer. Let's detect them earlier. So let's find blood biomarkers. C125 is elevated pretty early. So then, then a bunch of studies, including the PLCO and others, find that imaging is a barrier. It just doesn't work as well, maybe as C125. We still have to solve it. But until recently, there was no way to really kind of attack that. So now there's these nanoparticles. So you say, okay, let's find a locally specific cell surface marker. So we have to find a marker on the cell surface of a cell that's locally specific and not in the blood, so there's no background, okay? Great, so then you go up and say, let's go back to do early detection, but the question is, if you do that, you say, well, a few things hurt. Well, from the removing tubes, do we actually even know the fact that there's early late stage, or I like to say red versus blue cancers? If we called late stage cancer red and early stage blue, and I said, let's catch those red cancers earlier when they were blue, you might say, why would you think they'd be a different color earlier in time? So maybe the language we have for late stage is interfering with the fact that we really don't know if these things are early or not. A fist-sized early stage cancer isn't necessarily an earlier version of a millimeter-sized invasive lesion. And I think that's a risk that I thought I'm not going to race the rest of 15 years of my failed career on. But also, the fact is, once you solve this problem of attaching to the cell surface, well, the thing is, there's all kinds of other things you can do. One of them is you can actually attach all kinds of things to this particle. You can deliver agents. You can actually attach them to a receptor. They get internalized. They can deliver small molecules. I'm working with Frank McCormick and people in the RAS cancer to try to find ways of delivering them that way. And so you can deliver ways, and you even put orthogonal different wavelengths of stuff, and you can get these in a spin and destroy any cancer cell, anything that they're attached to. And so if you did solve the imaging problem, what you would then do next is try to use that to solve the therapy problem. In fact, those same cell surface proteins might be identified by people who do therapy and use it as a target. So certainly, I think that there's an avenue there for low risk. It's certainly necessary for early detection, but if you solve it, there's so many other opportunities there because they're just so versatile. Of course, they've never been injected in a person, but they've actually done pretty well in curing mice. Well, not really yet, but someday they will cure mice. And so, this is kind of where my career is going. So we do a lot of the stuff now in this kind of profiling the cell surface with some nucleic acid technologies now, actually. And while they'll be useful, I conveniently use early detection as an excuse to get funding. That nobody should quote that during a study section. But the thing is, it's really just a way of kind of being very, kind of hedging bets, which sounds like a very crude way of doing research. But I think the key thing is that if you do feel like early detection works, if you find a great marker, well, it can't ever work unless you have imaging done. So this needs to be solved. Next slide. Yeah, this kind of gives kind of a larger picture. But it kind of basically says, well, what's an evolution of this, an actual evolution? If you could do imaging, once you have those things done, well, then you can actually use them for a cure, because imaging is a very low bar. The toxicity thing isn't very high because you're not trying to destroy anything. Well, then you can go to cure. That can have a lot of toxicity, right? But it turns out things work in the low. Then all of a sudden you can actually prevent cancer. So there's a lot of work in the kind of precursor lesions. Well, if you turn to a precursor lesion, you can define it. Well, you can actually, quote, image those. But you don't have to even image those. You can just kind of try to destroy those cells, either by chemopreventive stuff or even just behavioral prevention. Deborah, shout out to you. How about that? Behavioral people in the room. And so I think there's, it's still risky. I don't want to say this is a panacea, but it seems to me that it's just something that needs more attention. And I think the attention isn't necessarily building these particles. A lot of people in this field are kind of like analytic chemists and proteomics. They're great in developing technology, but they're not necessarily focusing on using them, which actually requires a bit more kind of focused skill. And so if you go to the next slide. So the final thing, I'll summarize by other kind of arguments by, given the time scales, someone told me, don't go there and give a typical, I'll use my wording, typical statistician's talk where you walk into light and spread darkness. But what I actually think of is that this is really kind of an optimistic view of advancements in therapy and other technologies that, the time scale, imagine if today we found some good markers. We wanted to deploy them out and get them involved in an early detection program. It might take 15 years or so. I mean, the Ian Jacobs' trial started like 20 years ago, right, 15, 20 years ago, and that, it may not work. And so the question is, you have to basically say that that's an avenue. The successes in therapy and other avenues in prevention will only diminish the cost effectiveness of doing screening, which is really pretty hard already in the first place, given it's a rare cancer. But you also have to say, well, to suggest that after a 15, 20-year period, that's still going to be very valuable, it has to be a very pessimistic view that any other approach is going to work or not. And so I think actually it's kind of the optimistic tone rather than, and if you see Garnet, point out to her that I gave an optimistic tone to this, right? Again, I don't think we should give up on early detection, but maybe we have to identify people at risk for moving the tubes. But I actually say there's two friends of mine who had children, and while they were there, they told their doctor, hey, well, C-section, so we'll have the, tie the tubes. I said, well, why don't we just remove them? It would lower your risk of ovarian cancer. And I think it's probably, I talked to a couple of docs, I said, yeah, they're just routinely asking people. So this idea that people are going to move their tubes, it's happening. It's like PSA. People adopt it before there's a trial. So if that works, and I actually think it will tremendously, the thing is, it's certain that maybe what we're going to find out is that the problem will go away on its own without any of our support. And we need to turn our attention to things that are actually way more productive. And also the fact is that, is there an early curable stage? I think Beth was the first person to tell me that maybe there wasn't. And so, what would I recommend doing? If I had a lot of money, what I would do is I would actually do studies of early natural history to find out whether there is one, but more importantly, to find things that you can use for prevention, right? I would also fund research in optimizing nanoparticles for the ovarian cancer environment, microenvironment, right? Because there's actually a lot of work. So the thing is that instead of having somebody find a target and then trying to optimize it, well, the question you could fund people to say, engineer something, show that this works in that environment. And studies of like what mouse model is best for mimicking the microenvironment, not the pathology, but the microenvironment. And then research on manipulating the microenvironment, which actually will help not only deliver these things, but also drugs and other therapies, and also be useful possibly for early detection as well. So I think this is kind of like, a safer bet, but it also kind of just takes a step back and say, where are we in the world? And if we started over again, would we think that early detection is the place to go? And I think this is just an argument for doing more, kind of more boys with toys. And the thing I have to say is I don't want to be looking at a world where I have to kind of read people talking about novel nanoparticles anymore, but other than that, I can't see a downside to it.